Welcome to screencast session. Now we are implementing the Bellman-Ford algorithm. It is also single source shortest path algorithm, but it allows that edge with negative weights. It's taking two parameters, the adjacency list and starting vertex from where you want to traverse it. We are doing initialization. This time we want to do that infinite. So that infinite in using the float constant of that Python, it's taking a constant of infinite that is initialized to infinite, and we were creating one distance dictionary. This dictionary, it is empty initially. We want to do that initializing of that each dictionary value. So that is in, so adjacency list of that keys, each key dictionary that we want to initialize the distance is that infinite. So that distance of the v is initialized with infinite. So infinite is already calculated in the fourth line. Now let's do that computing the particular shortest distance. So in the Bellman-Ford, we want to use that n-1 edge relaxation because it allows you that negative weights until all the values are stabilized. We want to repeat that n-1 edge relaxing. So it could be that outermost loop. We are repeating for I in, so the W list of keys. So the W list of keys. So this is called n-1 edge relaxing loop. So now we want to check that, so whether it is u to v is having that optimizer value is available or not, using two nested loops here for u in, so W list of keys. So here we want to get the distance from u to v. We are doing a nested loop here, two nested loops of course, for v in. So of course we want that u to v distance also I wanted. So in, so W list of, because it is having a tuple of two values, so that's u. So that from the u to v we are getting the distance also. So similar kind of updating. If existing distance is of the v is greater than that calculated distance using that u. So that we are checking if, so the existing distance of v, if it is greater than, so the distance of u plus d, whatever new computed distance is smaller value. Of course initially it is infinite. Infinite is definitely, you know, that it is. And sorry, I didn't do that. The starting vertex initializing of its distance. So distance of s is initialized to 0 because initially starting vertex is having reaching distance is 0 because 0 is having 0 because that's going to be starting vertex. And we are updating the distance of the v, which is a new computed value. So by adding that current distance from u to v. So finally we got that result into the distance. So let me return it, return distance. So the graph which you are using is the same input. You can see that this graph is used in your GitHub notes. There is a -4 negative edges available, -1 is there, -2 is there. Bellman-Ford will available and it is able to compute the shortest distance even negative weights. But negative cycle is there means it will report that. So there is a negative cycle, the values are not stabilized. So this is the same input you have taken. The number of vertices are 8 because 0 to 7. And we created one particular adjacency list from this 40 line number to 44 and we call the Bellman-Ford. So let's run this. Yeah, there might be some kind of syntax error. Yeah, got it. So we are getting a tuple of value. It's not having colon symbol. The tuple of value is u, v and d, but d we are adding. So let me run again. Got it. So if you can see that what is the distance between that 0 to 1 is 5. So let you check it how it is 5. So you can check it this graph. The 0 to 1 there is a path, it's a direct edge is available 10. So 0 to 7 it is 8, 7 to 6 is 1, so it's 9, and 9 minus 4 which is 5. So reaching via 7 and 6 from 0 to 1 is smaller distance, comparatively a direct edge called that 0 to 1 direct edge is 10, but we are taking the shortest one. So this is that, you know, Bellman-Ford. it's working even you have the negative edge weights. So hope you got it. So thank you very much. Have a nice day.